Good morning, scholars. How are we doing today? Today, we're going to talk about motion. We're going to describe motion in all of its different ways. So, let's kick this show off here. See there, we've got a couple of dolphins jumping out of the water. Looks like fun, right? Let's go, man. Let's make a field trip. Let's go to the beach and let's go swim with the dolphins. Sound good? All right, so let's talk. Aristotle was a philosopher who lived in ancient Greece, 384 to 322 BC, and he was one of the first recorded ones to make some scientific observations on motion. He came up with two types of motion, natural motion and violent motion. Natural motion was such as a thing that occurs when like leaves are falling from a tree just naturally, like you see in the picture on the left. Violent motion, he described it as an outside force such as wind or someone shaking the tree like you see in that hurricane force winds there. And there you have Mr. Aristotle. But then along comes our buddy Galileo. Galileo truly was ahead of his time. Galileo lived a couple thousand years after Aristotle, 1564 to 1642. What did Galileo do? Like I mentioned, Aristotle's views on motion were accepted for about 2,000 years. Galileo studied medicine at the University of Pisa, so he started off wanting to get into the field of medicine. And then he discovered he had a passion for something else, mathematics and astronomy in particular. So he started observing things around the world. A very observant fellow, much like Aristotle, except Galileo observed the night sky. You noticed how the stars and the planets moved. And at that time, as we have discussed before, there was the geocentric theory. And the geocentric theory said that the Earth was the center of the universe. Galileo didn't agree with that. And the reason he didn't was because of his observations. So he decided that it wasn't just good enough because he understood that you had to be able to prove something, or in this case, disprove the geocentric theory. So he started performing experiments, such as from the Tower of Pisa, and in his experiments he showed that only an initial motion is needed. For example, if you're in space and I launch a space shuttle and it takes off into space, once it's going in space, because there's no air resistance, I can shut my engines off and it's just going to keep on going. So all of his ways of studying observations about how the planets and the stars and the moons moved across the sky and performing his experiences, he had to come up with a thought process and a step-by-step method of trying to disprove the geocentric theory. And this became known as the scientific method. This launched the era of modern science, because before him no one had a clear, concise, step-by-step way, as far as we know, according to recorded history. He was the first one to come up with a clear and concise recorded way of using the scientific method to disprove something. And so in his experiments he stated the concept of inertia, and inertia is the tendency that things have to resist a change in movement. One more time. Inertia is the tendency that things have to resist a change in movement. So if you're laying in bed this morning and you didn't want to get up, that would be a form of your inertia. Or you're riding your skateboard down the street and you're flying along, you're doing good. You don't really want to stop, but you have to when you come into the red light. But you'd rather keep going. Inertia, the tendency that things have to resist a change in movement, whether they're going or they're not moving. So in order to continue his experiments to disprove the geocentric theory, he took a spyglass, and you can see there on the table next to his right elbow, you see a spyglass behind that book. Spyglasses, if you've ever seen Pirates of the Caribbean, they were the ones that the captains used to watch ships far off in the distance. So he took spyglasses and he modified them to come into a telescope. Now, and some people have passed around the idea that Galileo invented the telescope. That's not accurate, necessarily accurate way to say it, because there were already spyglasses. Just that people really hadn't used them very much to look at the stars and to observe the planets. So Galileo took them and he realized that he needed to see things a little clearer. He modified it and came up with a better one, and he called it the telescope. With his telescope, he was able to discover some amazing things. He was the first one to discover that there were mountains on the moon. Previous to this time, people had some really weird ideas about the moon. They thought the moon was made out of cheese because all the holes in it, like Swiss cheese, and they had a lot of bizarre, weird ideas. Because we just didn't know. People were left to their imagination. But with his telescope, he was able to verify and prove that there were mountains on the moon. He also discovered that the planet Jupiter, had moons. But he could only see the first four, the largest of the moons. And we know now that with modern technology, modern telescopes, and the space telescope, Jupiter actually has 69 moons. But when we get into astronomy later this year, we'll talk more about that. But Galileo was the first one to discover that there were moons around Jupiter. All of this experimentation and all of this stuff, he came up with some pretty concrete evidence, conclusive evidence to prove that the geocentric theory was not true. However, the paradigm or the accepted belief of the time, most especially put forth by the Roman Catholic Church, was that the Earth was the center of the universe. And they didn't like to have their position and their belief challenged. And so Galileo was familiar with another man named Copernicus, who was an astronomer before him, a Polish astronomer. And actually, Copernicus is the first one we know of in recorded history to challenge the geocentric theory. But Copernicus was put under house arrest and given a real hard time for what he did. So Galileo knew this, and so at that time, everyone published scientific findings and things in Latin, because that was the language of the Roman Catholic Church. You published things in Latin. And so Galileo, trying to avoid some troubles and problems, and he just wanted to get his scientific evidence out there for people to look at, he published his findings in Italian. This upset the authorities of the time, and so they got copies of it, and they realized he was challenging the theory of the geocentric theory, the predominant theory of the time, which challenged the authority of the leadership of the Roman Catholic Church. And so they put him under house arrest, where he stayed for the rest of his life. But we can talk more about that later. Nonetheless, Galileo's findings that he had published, they tried to gather them all and destroy them. They were not successful. Some of them survived, and we have some today. And interesting enough, in the Vatican, there is a copy of his original book, Mathematica de Principia, that shows that the geocentric theory was not correct. So let's talk now what he said about inertia. Like I said before, we said inertia, the tendency that objects have to resist a change in movement or motion. And so Galileo, this is the experiment he did, experiment on the old idea. So you see there the Leaning Tower of Pisa. This is the one experiment he did. You see there's a large iron ball and a small iron ball. And on the left was Aristotle's idea that because the larger iron ball had more mass, it would fall to the ground first. Galileo took that large iron ball and small iron ball, dropped them from the Leaning Tower of Pisa on the right, and they hit the ground at the same time. Why? Because gravity pulls on everything on Earth with the constant force. And inertia, everything has inertia. So you can see there on the right, far right, there's an air tube, glass tube with air in it, and a glass tube with a vacuum. So one of the other experiments that Galileo did was he took a coin and a feather to further his experiment of dropping two objects. And in the air, you drop a feather and you drop a coin. The feather, obviously, because it's shaped like a feather and it's going to catch the air resistance, it's going to float on the wind. So the coin, if you drop a coin and a feather in the air like we breathe, or what they left in that cylinder, then the coin would hit the ground first. However, if you take all of the air out and create a vacuum like they did in the glass chamber on the right, then you drop the coin and the feather, something interesting happened. Just like his experiment with the Leaning Tower of Pisa, the coin and the feather hit the ground at the same time. Okay, now let's talk a little bit about inertia. Class discussion. Does inertia only apply to inanimate objects? How much inertia do you have? So let's look at the picture right in the middle there. You got an astronaut on the International Space Station, and he's floating above the Earth about 250 miles, and there's still a little bit of gravity, but there's not as much. So that's why they can have what they call a weightless feeling. But the reality is, on the space station, it's not correct to say that they're in a zero gravity environment. They are in what's called a microgravity environment. There's very little gravity, but there's still gravity. And how do we know that? Well, the space station would not stay in orbit around the Earth if there were no gravity to keep it being pulled towards the Earth. How does it stay in orbit? Because if it's got forward velocity, well, no, it's got forward acceleration, it's got forward momentum, keeping it moving around the Earth so fast that the gravity can't pull it down. But there's enough gravity to keep it from flying off into space. So that astronaut in that picture, if you've ever seen videos of the astronauts doing spacewalks on the space station, it looks like you can see the Earth moving below them, and it looks relatively peaceful, like the Earth is moving kind of slow. But the reality is, just like the Earth, those astronauts, in order to stay at 250 miles above the Earth, they have to be moving at a high speed, and they are traveling at about 17,000 miles per hour. So look at that picture again. You see him standing on that platform. You see the red rope. He's tethered to the space station. If he were not, what would happen? Well, because the space station has more momentum than him, because it's larger than him, and they would be moving around the Earth and he would float off, and he would not stay with the space station. So they tether the astronauts like that so that they don't go flying off into space. But now look at that picture again, and you see the thin blue line. So you can see the oceans below, and you can see some clouds, and then you see a hazy line along the edge of that's Earth's atmosphere. Our atmosphere is kept in place by the gravitational pull of the Earth, but the air around you that you don't really think about very much, it has inertia as well. Anything that has mass has inertia. So let's go on to the next one. Let's talk more about mass and weight. Sorry, which is which? Okay, so there's 5 things here, 5 different characteristics, and what I want you to think about as I read them, which one applies to weight and which one applies to mass. Okay, the force upon an object due to gravity. Which one is that? Weight. If you said weight, then you got it correct. Weight is determined by the force of gravity. Okay, so mass, the second one. Number 2, the quantity of matter in an object is its mass. How much stuff something has in it is mass. And then mass is, in the scientific world, we like to keep things consistent and not have too much things that can get all messed up and wonky. So we measure mass in kilograms. You might hear people say, oh, you measured the mass in weight. Well, in pounds, you could, but it's not correct to do that in science. In science, you're supposed to measure mass only in kilograms. Now, the mass also determines an object's inertia. So think about it this way. You got a skateboarder rolling down the street, and he's going downhill. He's moving pretty quick, okay? And there's also a moving truck parked on the side of the street. That moving truck is not moving, Which one has more mass? Well, the moving truck, obviously. It's much larger. It can put a lot of more stuff or matter inside of it. So it has more mass. But it's not moving, so it doesn't have any momentum. The kid on the skateboard rolling downhill, he doesn't have as much mass, but he has more momentum. Do they both have inertia? Yes, they do. The truck, larger mass, has more inertia. So that's why number 5, we say that mass and weight are directly proportional to each other. So what does that mean? How does that work? Let's take a little bit more closer look and think about this. You see here the part of the solar system. You see some of the planets. And what would your weight and your mass be on another world? Would they stay the same? Would they change? So think about what we just said. Would your mass and your weight be the same on other worlds? No, they would not. Because your weight is determined by the gravitational pull of what you're standing on. So, and what makes something have more gravity? Same thing makes it have more inertia, more mass. The more massive an object, or in this case, the planets, the more massive the planet, the more gravity it will have. Okay, so but there's going to be something. I'm going to throw you a curveball here in a little bit about that. But let's think about this. So, for example, on the sun, this number you see is compared to the gravitational pull of Earth. Your mass would not change, but your weight would be 27 times as much as you are like now. Let's say that you weighed 100 pounds. If you could stand on the sun without being vaporized and burned up instantly, if you could stand on the sun, your weight would be 2,700 pounds, because that's how much more gravity, how much gravitational pull the sun has compared to the Earth. Okay, all right, so that's the sun. Again, your mass would not change on any of these places we're going in the solar system, but your weight will change. So, for example, the moon. Moon is a lot smaller than Earth. So therefore, it has less inertia and less gravity. The gravitational pull of the moon is 0.16 that of Earth. So your weight would be 0.16 of what it is on Earth. Your mass would not change. Mercury. What would your weight be on Mercury? 0.38, because Mercury is a little bit bigger than the moon, but still smaller than the Earth. Venus, pretty close to Earth, so your weight would be 0.91 times that what it is on Earth. Your mass, not changing, just the weight. So, and then Earth, of course, your weight on Earth is the same as it is always. So 1 times 1, and your mass would not change, but your weight would still be 1 times what it is right now. If you weigh 100 pounds, 100 pounds times 1, you still weigh 100 pounds. Mars, a little bit smaller than Earth. Now, you're going to see some patterns here. One of the things that you need to do with science is you need to start to recognize patterns. Those of you who have well, probably most of you have never had me for geometry, but maybe a couple of you may have had me for when you were, I did teach some 8th graders geometry last year. I know I am not teaching geometry this year. However, you may have remembered that we talked about proportions on Earth and in gravity and in geometry. Anyway, Mars is 0.38 times as much as Earth. Now, so the pattern, what I was saying about geometry is I told you to recognize patterns. Okay, so Jupiter is much bigger than Earth. You'd weigh 2.34 times more than you do on Earth if you could stand on the surface of Jupiter. Saturn, wait a minute. Are you sure that's right, Mr. Plum? Saturn is huge compared to the Earth. How come we would only weigh a little bit more on Saturn than on Earth? What's going on there? Did you get that typed in wrong, Mr. Plum? Nah, it's correct. So, and we're going to come back to that in a second. So let's take a look here. Let's keep going. Uranus, what? You'd weigh less on Uranus than you would on Earth? Nah, that can't be right. Uranus is big compared to Earth. How come on? What's going on here, Mr. Plum? Okay, hold that thought. Keep thinking. Neptune. Neptune's also much larger than Earth. But what? I'm going to weigh more on Neptune than on Saturn? What's going on, man? Yeah, you're crazy, Mr. Plum. Something's messed up here. Obviously, Neptune is smaller than Saturn, or is it? Let's continue. Pluto, 0.06. Okay, so now that you're trying to, you don't understand what's going on, I'm gonna answer those questions for you in just a minute. So don't get all freaked out on me. Don't be too confused. I'm gonna explain it to you in the next slide. But before we do that, let's see if we can see some patterns here. So the pattern being, if Mars and Mercury, according to this, they have about the same weight, 0.038 times the weight of Earth on Earth. Does that mean that Mars and Mercury are the same size? They're not. Mercury is smaller. And why? We're going to get there. Jupiter, 2.34 times. But Jupiter is known as the king of the planets, and it's massive compared to Earth. And you're going to see how much bigger in just a minute. Same thing with Saturn. But why is Saturn only about a little bit more than Earth? And Uranus, which is smaller than Saturn, how come I'm sorry, Neptune, which is smaller than Saturn, how come I'm going to weigh less? And Uranus is still big compared to Earth. How come? Well, next slide will answer that. But in case you want all these numbers I'm showing you here, if you want to wonder where I got them from, you see there at the bottom, it says exploratorium.edu, RONH/weight. If you input that and you go to that website, you can put in your weight and it'll tell you what your weight is on all of these places in our solar system as well as places outside of our solar system. So it's a pretty cool website. I thought you might like to see it, have fun, share it with your parents, whatever. Let's go to, so on the moon, there he weighs 0.16 what he does on Earth. Let's go to the next one. Density and volume. Now here's the answer to the question that we had that I created for you and maybe confused you a little bit. Jupiter only 2.34 times, but look at this picture here. This is a 2-scale picture. This is comparing the sizes of the 8 and, well, okay, we're going to leave Pluto in there even though Pluto has been officially declassified as a planet. We'll get into that later. Don't worry about it right now. But you can see a size comparison here. And actual size of diameter of each of the planets, this is the known diameter with what we have with our instruments that we can measure. Obviously, we have had spaceships fly to Jupiter, Saturn, Uranus. We've had a spaceship fly to every planet in our solar system, even Pluto. New Horizons has visited that. And so this is pretty accurate how large in diameter the different planets are compared to Earth. Now let's look at Jupiter. It's huge compared to Earth. How come on Jupiter you only weigh 2.34, that's what you do on Earth? And Uranus, you actually weigh less than on Earth, 0.92. And look, Saturn, and we took the rings off just so you could see them better in this picture. Saturn has a bigger diameter than Neptune. Why do you weigh more on Neptune than on Saturn? And then, of course, you can see the planets. And like we talked about how Mercury and Mars have approximately the same weight. But you can look there. There's Pluto, and the next two is Mercury and Mars. You can see that Mars is bigger than Mercury. So what's going on is density and volume. So volume is a measure of the space inside a given area. And we measure it in cubic millimeters, cubic centimeters, cubic meters, cubic liters, etc. Okay, again, we stay with the metric system. Okay, now density is a little different than volume. Density is the total amount of mass divided by the volume. So, for example, imagine if you had a box that's approximately, you know what? Here, hold on a second. I got a box for you. All right, so let's take this box right here. So we got this clear box. And this clear box, right now, there's nothing in it, but is there? There's air in it, okay? Now, if I took this box and I filled it full of gold, what's going to be happening? Well, first of all, you might try to rob me because that's a lot of gold, but hopefully you wouldn't. Anyway, it's going to weigh a lot more than it does now. Will its mass have changed? Yes, because you got more stuff inside it. So I fill this full of gold, and it's going to be more mass. However, the volume will not have changed. The volume is the total space, the amount of stuff you can put inside here. The total volume of this cube won't change no matter what you put in it. But the density will change. Okay, so that's why how you can define density. If I filled it full of gold, it's going to have way more density than it does right now because it's just got air in it. Okay, so that will explain to you why you can be on Neptune, which you can see in the picture right there. Neptune is smaller in diameter than Saturn, but Neptune is more tightly compacted. The gases on Neptune are more tightly compacted. We're not 100% sure why. We've only flown spaceships around. There's only been 2 spaceships that have flown past Neptune, Voyager and New Horizons, and they just did flybys where they took pictures and stuff, and we were able to, with those pictures, measure the diameter, measure what the gas atmosphere is, and some of the instruments could measure the density. That's how we know that Neptune has more density than Saturn. Even though Saturn is larger in diameter, it's more fluffy, if you want to put it that way. It does not have as much mass in it as Neptune. So therefore Saturn, you could stand on the surface of Saturn, but you really couldn't because it's a gas surface. We don't know where the actual solid surface of Jupiter, Saturn, Uranus, or Neptune is. But we do know that those are the gases that extend out to that volume, to that diameter. So if you could actually stand on the surface of Saturn, though, you would weigh less than you would on Neptune because it has less density, less mass. So that's why Jupiter, even though Jupiter is so huge compared to Earth, you're only going to weigh 2.34 times what you would weigh on Earth. You would think, as large as Jupiter is, that has that much more gravity, you weigh a whole lot more. But no, because it's not as dense and solid and compact as Earth. Which is why when we get into astronomy later on, you're going to find out we call the Earth, Mars, Mercury, and Venus, we call those the rocky or terrestrial planets. Jupiter, Saturn, Uranus, and Neptune, we call those the gas giants. And Pluto has its own classification. But we'll talk about that when we get to that part of astronomy. Okay, now let's talk about something else. Net force. No, it's not a new division of the military. I know we got the Space Force and so forth. The net force is not that. What net force refers to is the total amount of force acting upon an object. And then you have equilibrium, which is a balance of forces in opposite directions. And then you have a Newton, which is the scientific unit of force. Okay, so net force is something we're going to talk more about in the next slide. But we need to define what a Newton is here at this point. So 1 kilogram weighs 9.8 newtons. Why do we say it weighs 9.8 newtons? Because remember, we talked about the force of gravity. And 1 newton is the force of gravity. 1 times the force of gravity pulling upon you on Earth is 1 newton. Okay? But 1 kilogram weighs 9.8 newtons. So in physics, the standard unit of measurement of mass is the kilogram. And the standard unit of measurement for force is the Newton, or a capital N. On Earth's surface, a 1 kilogram box of any material has a weight of 9.8 newtons. So remember, weight is a function of gravity. Different worlds, you have different gravity, so you weigh differently. So the average force that the Earth's gravity is pulling on everything on Earth is 9.8 meters per second squared. We usually just round this up to 10 newtons, so we can say that the force of gravity, or gravity on Earth, is 10 meters per second squared. Okay? Okay, so this brings us to the concept of net force. So let's talk about net force. In the picture on the right, you see some people having a tug of war. 2 people on the left pulling with 320 newtons to the left, and on the right, the 2 people are pulling with 300 newtons to the right. So the net force, like we talked about before, is the total amount of force acting upon an object. So in this case, or acting upon a physical reaction. And so in this physical reaction of the tug of war, the net force, to calculate it, you just take the difference between the two. So you take 320 newtons minus 300 newtons, and you've got 20 newtons of force, and it tells you which direction. So it's going to the left. So you could say then that the net force in this has a velocity of 320 newtons to the left, because velocity is movement in one direction. Okay, so now let's go look at the picture on the right. You have, in the bottom one, you still have an unbalanced force. Okay, what is equilibrium of forces? Equilibrium of forces is still a net force, but it's when the net forces are balanced, so that you have an equal amount of force pulling in opposite directions or compressing. So the forces could be compressing or they could be pulling. So the net force on the left, the top one, the net force is 0, because 300 minus 300 is 0. So the net force on the left, the picture on the very top, where they're both pulling in opposite directions with 300 newtons, that net force is 0. 300 times minus 300 is 0. And when you have 0 net force, you have equilibrium. Okay? And then the bottom picture on the left, you've got the people on the left start pulling a little bit harder, and they're pulling with 400 newtons to the left, and the people on the right, they miss the cue, and so they're still pulling with 300 newtons. The bottom picture, the people on the left are going to win the tug of war because they have an unbalanced force. They have more force being pulled to the left. So some other things that we commonly think of where this comes into place in your everyday life is we have scales. There's a scale that you measure weights, like if you go to the market, and then in the middle you've got a bathroom scale or a kitchen scale, or wherever you guys weigh yourselves or your parents weigh themselves. And then how does that kind of scale work? Well, on the right there you see a spring in its first condition that's just sitting there, no one's standing on the bathroom scale. And the second spring in the middle, the person has standing on the scale, and that spring is being compressed, is being pushed up by the force of the earth and pushed down by the force of the person standing on it. And when those forces balance, the dial on the scale stops, and that tells you that that person weighs approximately 120 pounds. You could say 120 newtons, just if you want to keep it straight for what we've been talking about. When you reach an equilibrium of forces, that tells you what you weigh. Now, you may be familiar with the scales at the doctor's office. They're slightly different than this. The scale at the doctor's office has got a thing like this, when there's a weight that they slide back and forth, and when that weight, they get it balanced to it stops, then it points to your weight. Now, some doctor's offices you may have gone to have started using digital scales. They work pretty much the same way. They still have a spring in it, but instead of having that balanced bar, they just have a spring. But it still works the same way. When you reach your equilibrium of forces, that tells you how much you weigh, because weight is a function of gravity. And the force of gravity pushing up and pulling down on you, and you pushing down at the same time, you reached an equilibrium of forces. That, ladies and gentlemen, is describing motion. I hope you enjoyed it. And I hope you were paying attention and took some notes, because there's going to be some questions to follow. So keep moving, and remember, science is cool.